Meet Bad Boys and Associate, responsible for the design of the San Onofre Desalination Plant. My name is Ryan. I'm the project manager for the design team. On the left here is Lee. He is responsible for the geotechnical operations, and he doubles as an associate to Daniel King, our structural engineer. Next are our water resource engineers. Giuseppe was responsible for specifying initial water quality and the seawater reverse osmosis process. Mackenzie determined the appropriate intake and pump design. In response to rising demand and depleting water supply, the Water Authority began evaluating seawater desalination as a highly reliable local water resource in the early 1990s. The targeted goal for Bad Boys and Associate is to produce 55 million gallons per day of potable drinking water via reverse osmosis desalination. Based on the 2010 San Diego Water Use Report provided by the Water Authority, 45 mgd of water were consumed that year. If current water usage held consistent perennially, seawater desalination would account for 12% of the San Diego water supply, thus meeting the 2020 San Diego water profile. The process of optimizing the San Onofre desalination plant began with appropriately conducting a soil profile. The soil profile determined the site location chosen was suitable for the proposed plant design. After analyzing the soils, networking the intake and discharge follow suit. The design incorporates the utilization of an existing open ocean intake system at the San Onofre Nuclear Generation Station, or SONGS. Provided the assumption that environmental regulations are met, Bad Boys and Associate determined the existing open ocean intake system at SONGS to be the best option. Once the means for intake were determined, influent and effluent water quality parameters were identified. Based on numerous water quality studies, those influent and effluent water quality parameters were identified. Design of the reverse osmosis process began following the influent parameter determination. A specific step-by-step process is required to ensure the distributed water meets human consumption standards. The treatment process will consist of pre-treatment, microfiltration, a 2-pass RO system, and post-treatment. Lastly, Bad Boys and Associate designed the appropriate structure for the RO system. The most efficient structure is a simple steel structure composed of a triangle truss frame. An in-depth analysis of each project discipline is provided in the following report.
San Onofre is composed mostly of alluvial soils. The topmost soil surface is composed of varying types of clay, silt, and sand underlain by fairly solid bedrock at an average depth of 10 feet from the surface. In the figure shown, a map showing the locations and depths of the boring holes can be seen. Here we see a sample soil profile that was created based off of the soil borings. These borings were conducted using a combination of methods. First, a bulk sample was taken at the topmost part of the soil. Then, to drive through the deeper layers of soil, a combination of the SPT, the standard penetration test, the modified Cal sampler, and the Shelby tube sampler were used to determine the soil parameters. The SPT and modified Cal sampler are used to drive through non-cohesive soils, while the modified Cal sampler is able to take soil samples during the test. The Shelby tube sampler is used for cohesive soil, and like the modified Cal sampler, takes soil samples during the testing. The soil profile is composed of 3 layers, plus a topmost layer of undocumented fill. However, since the bottom 2 layers were composed of very similar dense, silty sand, they were consolidated into one soil layer for the purpose of simplification. The other soil layer was composed of dense, silty to clayey sand. In the case of an earthquake event, liquefaction must be calculated. After calculating the factor of safety for liquefaction analysis under a seismic event of magnitude 7.5, we determined that the soil layers will indeed liquefy as shown in the design report. With the first layer of soil having a factor of safety of 0.76 and the second layer having a factor of safety of 0.634, both below the limit of liquefaction of 1 for factor of safety.
Building a desalination plant next to a coastal power plant offers several economic and environmental advantages. The power plant's existing seawater intake and discharge facilities that provide water to cool the plant's turbines also could deliver water to the desalination facility and convey brine back to the ocean. Songs operates 2 independent cooling water intake structures to provide condenser cooling water to their 2 tower systems. Once through cooling water is combined with low-volume waste generated by Songs and discharged through 2 outfalls located offshore in the Pacific Ocean. San Onofre's ocean water system works with a screen intake tunnel. A 3,000-foot intake pipe begins with a unique velocity cap using a special design that causes fish to swim away. The pipe's opening is located at a depth and distance from the shore where the least fish are found. An innovative protective system diverts a small percentage of fish that enter the intake pipe to a catch basin where they are returned to the ocean. Songs only uses 5% of the intake water to cool their reactors daily. This excess of cooling water will be the basis of our feed water to supply our desalination facility. A feedwater pump station will be installed and employ pumps of the high-flow, low-head type to convey feed water from the onshore tunnel terminus to our desal plant. Brine, a concentrated salt byproduct of the reverse osmosis product, would also need to be discharged through a designated outfall tunnel in the Pacific Ocean. Brine has specific discharge requirements and must be diluted to nearly half its concentration or through an engineered diffuser system. Additional cooling water will be available from the power plant to mix with the brine, diluting the concentration of salts before it is discharged into the ocean. A similar onshore pipeline will convey concentrated brine from the desal plant to the condenser cooling water tank at Songs to mix with the brine. Although the desal facility has a source of dilution water, the excess outfall conduits at Songs are fitted with a diffuser structure to increase permeability. Proximity to the power plant will also reduce the cost of bringing power to the desalination facility. These factors all help reduce the environmental impacts and cost of constructing, as well as operating the desalination plant.